Hello everyone. In this video, you will learn the deep learning workflows implemented for well-log data in Geomodeling's products. In Geomodeling's software, we can make unsupervised log facies classification and supervised log facies classification. The supervised log facies classification includes rule-based log facies classification, build deep learning model, and predict facies log from deep learning model, and the bias classification. The deep learning workflow can be used to predict SBED near-wellbore upscaling results. SBED is one of Geomodeling's products which bridges the gaps between core data and full-field reservoir models. Our core-to-facies modeling and upscaling workflow in SBED allows users to integrate core-scale data and make facies models with small-scale heterogeneity to get results of effective directional permeability for the facies models, which will be used for large-scale reservoir modeling and simulations. The algorithm used in unsupervised log facies classification is self-organizing map, which will find out the number of clusters in the provided data based on some criteria. This is also called data-driven. In unsupervised log facies classification, users will decide how many numbers of classes they want to classify. You can launch unsupervised log facies classification command through the red button menu from the Wells node on the data tree view. This is the interface of unsupervised log facies classification. In this page, you can define parameters for log facies classification. First of all, there is a deep learning toolbox. You can checkmark the box if you want to use deep learning toolbox in the classification. And the second part is selecting wells. You can checkmark the wells for which you want to create log classification. And the third part is depth range control. You can select one of the options to define depth range. You can select well tops or specified MD for depth range control. And this based on multi-wells checkbox is for you to checkmark the box if you want to do the classification based on all selected wells. Otherwise, the classification will base on each well. And the checkbox all in memory, if this option is checked, all selected well data will be in memory and the calculation will be fast. If you try to do facies classification for a large number of wells, please uncheck this option. And next, on the top, you can see there are two radio buttons based on log template and based on log alias. If you choose based on log template, then you can choose input log based on log template. If you choose this option, only one log alias can be selected under each log template in each well. You can change log alias for each individual well using the log drop-down box in the selected well section at the left of the dialog. This based on log alias. This is to choose input log based on log alias. If you choose this option, all log alias can be selected without restriction of log template. For example, you can select different log alias under one log template in each well. And please note, when selecting wells, those wells don't have such logs will be highlighted in red color, and they won't be considered into the calculation. This part is for clustering parameters. This is to define the number of facies you want to classify. the error of calculation, and the maximum iteration. And then you can select to create a new well log or updating an existing well log. And the last is the MD setting, which is to define the sample MD and select sample interval from log or specified. After you set up all the parameters, you can hit OK, and then it will generate the facies log for the wells you selected. Different from unsupervised log facies classification, which is purely data-driven, supervised log facies classification needs users to provide the ground truth, which is to use the training data or other criteria. There are 3 different types of unsupervised log facies classification: rule-based log classification, deep learning model, and Bayes classification. The rule-based classification needs users to give some rules to classify the facies for well logs. Users can start rule-based log classification on individual well, or on a well folder or well group that contains a group of wells. This is the interface of rule-based log facies classification. You can define parameters for rule-based log classification in this page. This is a template for the facies log. You can click the drop-down arrow and select facies template to be used in the log classification. Related facies will appear in a facies classes box. And you can type a name of the log facies classification. You can use the drop-down arrow and select sample interval for the log facies. And this part is to check mark wells for which you want to create log facies classification. The facies classes part shows the facies for selected templates. You can click Add facies to add more facies, or remove facies to remove any facies. And you can also do the depth range control. You can select one of the options to define depth range from logs, depth range, or well tops. And this is the condition of facies. You can first click the facies in the facies classes box, and then define conditions for different facies one by one. The last is the checkbox to export statistics to an ASCII file. After you set up the parameters, you can hit OK, and then it will generate the rule-based log classification under the wells you selected. In the deep learning log facies classification workflow, users will provide some training data, for example, at least one facies log as the ground truth. The algorithm will find some relationship between the facies log and the input logs to build a deep learning model. The deep learning model can then be applied to other wells within the same geological setting. You can start the command from the right button menu from the well nodes on the tree view. This is the interface for building deep learning model. You can define parameters for deep learning model. First is the target well log for prediction. This is to select the target well log for prediction. In this case, it should be facies classification. And you can specify the data range. Control the data range of target well log. By default, it includes all data range from the selected target log. And this is to select the input well logs for prediction. This part is the depth range control. You can select one of the options to define depth range. This checkbox for normalization applied to data inside depth range only. If this option is selected, the normalization is only based on the well data within selected depth range. Otherwise, it will be based on the full range. At right, you can select the well for training. You can check mark the wells for which you want to select for training. You can change the log alias under each individual well using the drop-down menu. Then in the next page, you can define parameters for neural network training parameters. First of all, you can select a neural network type. The neural network type algorithm used is neural network pattern recognition, which classifies data by training a two-layer feed-forward network. The neural network topology is that the input layer is the input data, and the output layer is the target. You can add or reduce the hidden layer if you want. By default, it has two hidden layers. And this is a maximum iteration. You can control the number of maximum iterations used to train the network. MCE means minimizing cross entropy, which is the criteria for stopping the training. For validation and test data, you can divide data randomly or you can select none. And this part is to set up the percentage of samples used to do validation, testing, and training. For validation, this is a measure of network generalization, which will stop the training when generalization stops improving. The testing is to set up the percentage of samples used to do blind testing. This is an independent measure of network performance. And for training, this is to set up the percentage of samples used to do training. The network will adjust based on the training error. The validation fail is to set the maximum validation fail. You can hit Advanced button to set up more advanced parameters. For the training algorithm, this is scaled conjugate gradient. This is a network training function that updates weight and bias values according to the scaled conjugate gradient method. The weight change factor is the value determining change in weight for second derivative approximation. And the regular factor is the parameters for regulating the indefiniteness of the hashing. The last one is the minimum performance gradient. If the performance gradient falls below this value, the training will stop. You can click OK to start building the deep learning model. Then the results of deep learning model will be stored under the separate deep learning models folder under the wells. To check the performance of the training, you can run a performance analysis on the deep learning model and evaluate the results in a performance analysis window. In the performance analysis for facies classification prediction, it contains the following aspects: confusion matrix, ROC curve, importance, PD and SAE plot, training performance, and data. The confusion matrix describes the measurement of accuracy of classification for training, validation, testing, and all samples. There are two display modes for confusion matrix: the confusion matrix images and the confusion matrix tables. Confusion matrix image is more straightforward and easy to understand. The y-axis indicates true class, and the x-axis indicates predicted class. The value in each square indicates the percentage of each predicted class for each true class. For example, in this image, for training samples, 84.2% true class 1 has been predicted to class 1. This is the correct classification. However, 15.8% true class 1 has been predicted to class 2. This is the incorrect classification. And the color indicates the data percentage value. The higher the value is, the hotter the color will be. Confusion matrix tables include more details. The number in the right line square represents the predicted class, and the blue line square represents the actual class. The green filled squares indicate the numbers of samples that classified correctly for each class and its percentage in the entire sample points. And the pink filled squares indicates the number of samples that classified incorrectly for each class and its percentage in the entire sample points. The number in the orange line square represents the percentage of the correct and incorrect classification for each predicted class. The number in the purple square represents the percentage of the correct and incorrect classification for each actual class, while the lower right gray square illustrates the overall accuracies, the percentage of correct and incorrect classification in the entire sample points. The ROC curve stands for Receiver Operating Characteristic Curve, which is a graphical plot that illustrates the diagnostic ability of a binary classified system as its discrimination threshold is varied. ROC curve is created by plotting the true positive ratio versus the false positive ratio at various threshold settings. ROC analysis has been increasingly used in machine learning. It is used for evaluating the performance of neural network for facies prediction. If the curve follows on the diagonal part, it means completely random and no accuracy. The further the ROC curve away from the diagonal part, and the bigger the area covered by the ROC curve is, the better the classification will be. The importance of attribute is calculated based on the increase of the prediction error after permitting the attribute. The attribute is more important if the prediction error increases more when the attribute is permitted, which indicates the prediction model is more dependent on this attribute. For facies prediction model, the importance of each attribute is facies dependent. You can control the facies to display the importance of the attributes for different facies. For facies classification, the vertical number above each bar is 1 minus AUC, which means 1 minus area of related ROC curve. The horizontal axis indicates the index of input attributes. The importance is decreasing from left to right, with the attributes number on the x-axis, which you can match the attribute number in the attribute list and the corresponding facies on the right side. You can sort the attribute list by importance, NCA weight, correlation coefficient, and name. This is the PD and SAE plot. The partial dependence plot shows the marginal effect the attributes have on the predicted target of the neural network or regression model. It is a global method concludes the global relationship between the attribute and predicted target by considering all the cases. One assumption for this method is the attribute used for computing PD plot is independent of other attributes. Unlike PD plots shows the average relationship between the attribute and prediction. Individual conditional expectation SAE plots review the relationship for each individual cases, changing the attribute itself and keeping all other attributes the same. The advantage of SAE plots is that it can reveal the heterogeneous relationship that might be hidden in the PD plot. However, it also has a disadvantage that it might include invalid data points if the attribute is correlated with other attributes. The recommendation is to display PD plots with SAE plots together so that you can see the average relationship as well as the heterogeneous relationship between the attribute and prediction. In the PD and SAE plot, each plot displays the relationship between one attribute and the predicted target. The PD curve reveals the relationship between the attribute and predicted target by summarizing all the cases, which is this red line. Each SAE curve indicates the relationship between the attribute and the predicted target by averaging the cases within one single while. And the color of the SAE curve shows if the whiles is used for training, validation, or testing. You can see in this picture, the sample for training is indicated by this dark blue color. And for validation, it's represented by the green lines. And for testing data, it represents by the light blue color. You can toggle on or toggle off the while from the while list at right to see the SAE curve for that particular while. The histogram bar on the x-axis indicates the data density for the corresponding attribute. Hotter color means the data frequency is high within this axis range for the corresponding attribute. Colder color means the data frequency is low within that axis range for the corresponding attribute. From the tree view on the right side, you can control the plots, data type, input attributes, and data from different wells showing in the plot in this window. This shows the training performance of the prediction model, which is related to the parameters you set for the neural network model. It shows how the error, validation, and testing changes as the iteration goes. As you can see, the blue line represents the training, green curve represents validation, and the red curve represents testing. It also shows where the training stops, indicated by the vertical dashed line. Validation and testing data samples can be used for avoiding overtraining. In this training performance plot, the training stops at around 40 iterations, where the validation and testing error are relatively small. Although the training error continues decreasing over 40 iterations, the validation and testing error increases, which indicates overtraining. Using validation and testing data sample would let the training stops before overtraining. This shows the data spreadsheet of the input data, training data, validation, and testing data, including wells, original data, predicted data, absolute error value, and error percentage. This data can be copied, opened in Excel, or saved as CSV file using the button on the top left. Please note the input table for continuous and discrete target variable is different. The correlation coefficient is applicable only for continuous target variable. For discrete target variable, for example, facies, only the NCA weight can be calculated and listed for each attribute in the input table. After building the deep learning model, you can predict facies log for other wells using the deep learning model. Start from the right bottom menu. From the deep learning model, you can select Predict Well Log. This is the page to define parameters for Predict Well Logs. First of all, the deep learning model, this is the deep learning model used for prediction. And this is the input well log used for generating the deep learning model. This is the predicted log template. And this is the predicted log alias name. You can control the minimum and maximum value for the predicted facies log. You can select the wells for which you want to create log classification using the blue arrow from the tree view. If you want to fill existing facies log instead of creating new facies log, then use the drop-down menu to select fill-based log curve. You can set depth range by selecting one of the options to define the depth range. You can click OK, then it will predict the facies log for the wells you selected. Bayes classification is a non-parametric statistical classification based on Bayes theory. Unlike parametric statistical classification that has non-mean, variance, and covariance and unknown distribution patterns for most features, non-parametric statistic classification is data-driven. The problem we are going to solve using Bayes classification is making log facies classification with given well logs. This is one of the workflows of supervised log facies classification. Unlike deep learning supervised log facies classification, Bayes classification based on the results of cross-plotting. Bayes classification calculates the joint probability or conditional probability for the data points, making the classification more meaningful. Bayes' theorem describes the probability of an event with prior knowledge of other conditions' probability. The mathematical equation is shown as this. It's a framework that converts our prior experience to posterior distribution. In our case, for example, if A represents a facies, then PA is the probability of the facies. B represents the seismic attribute, then PB is the general probability of the seismic attributes. PB/A is the conditional probability of the seismic attributes given the facies. If we know the general probability of facies, which is PA, and the distribution of seismic attributes for each facies, which is their conditional probability PB/A. By given attributes, We can then calculate the probability of the sample belongs to the facies by transferring the prior information as well as the conditional distribution to the posterior probability. We achieve the purpose of classifications. For the workflow of Bayes classification on well logs, we are going to calculate the facies probability with given well logs on the wells. The facies is corresponding to the maximum posterior probability, whereas P is corresponding to the probability density function. Firstly, the probability density function, PDF, for different facies with given well logs can be estimated based on the training model cross-plot of well logs and the facies log. Then another cross-plot of the well logs on the other wells will be made, on which the training model will be applied. The prior proportion of each facies can be given by users who have basic understanding about the facies distribution in their interest area, or based on the training model. Given the probability of attributes for each facies is constant, the facies conditional probability can be calculated based on the Bayes equation. There are two workflows to make Bayes classification. One is 2D Bayes classification, another is 3D Bayes classification. 2D and 3D Bayes classification is a supervised seismic facies classification workflow based on 2D and 3D crossplot, and it can be applied to stratigrade, interval, horizons, and well logs. And the workflow of 2D and 3D Bayes classification on well logs includes the following steps. The first step is on one well or some wells, cross-plot the well logs and use the facies log as the facies axis for the training model of Bayes classification. And then next, on another well or other wells, cross-plot the same well logs as that of the training model. The last step is to start the Bayes classification in the crossplot window from the second step. And next, I will take 2D Bayes classification as an example to illustrate the Bayes classification workflow. The 3D Bayes classification is similar, but it is based on the 3D crossplot. So, starting from the well, right-click on the well and select 2D crossplot. You can cross-plot the well logs and use the facies log as the facies axis for the training model of Bayes classification. So in this page, you can select X and Y axis for the 2D crossplot and use the facies classification as the facies axis. It will use the facies classification automatically as the color to color the crossplot points. And then before the crossplot window opens, it will open a dialog asking you to estimate the probability density function. You can create 2D probability density function for each facies and all points. If you don't do that in this step, you can also create 2D probability density function after the 2D crossplot has been created by going to the crossplot data tree view and right-click on the 2D PDF folder and select New 2D PDF. The 2D PDF for each facies will be created if you select to generate the 2D PDF for each facies. And you can select them from the 2D PDF folder from the crossplot data tree view to display them in the crossplot. When you display the 2D PDF for each facies, you can also see the 1D PDF of each attribute displayed on the histogram along the X and Y axis as the dashed line colored by different facies. In default, on the crossplot, the 2D PDF is shown in contours colored by different faces. You can right-click on the PDF on the list and select View Surface to display its surface. Edit contour parameters allows you to edit the visualization properties of contours. You can also change the detailed visualization properties of the 2D PDF by double-clicking the 2D PDF on the list. In default, the transparency parameters are enabled for the color map, and you can manually edit the transform curve on the histogram and observe interactive and quick update on the crossplot. And the second step is to make 2D crossplot on another well or other wells. So you crossplot the same well log as that of the training model. But here you only select the X and Y axis and don't select the facies axis. In the crossplot of the well logs, you can select Bayes classification training model built from step 1. In the crossplot window on the top, there is an icon showing Bayes classification. You can click that. And then in this dialog, you can select the crossplot you generate from step 1. Then a dialog will show up to let you specify a prior probability for each facies according to your own knowledge or experience about the facies distribution in the area. Or you can leave it as default. These default values are calculated based on the facies log. Then after you click OK, the training model will be applied on the current crossplot through Bayes classification. The data points are classified into different faces with given well logs. The posterior probability for each facies and the facies object from the Bayes classification will be automatically generated and saved on the tree view under the corresponding object while you started the process. You can observe them in a well section window. The last workflow I want to introduce in this video is to predict SBED near-wellbore upscaling results. SBED near-wellbore upscaling takes a lot of time. To save time and improve efficiency, we can predict SBED near-wellbore upscaling results from well logs using deep learning model. Before we train the deep learning model, we need to build SBED near-wellbore model for few wells to get some SBED near-wellbore upscaling results as the training data. For the training of the deep learning model, we can use petrophysical logs, core plug logs, or any other logs with the SBED near-wellbore upscaling results as the inputs. We can convert the upscaling results to logs and train them with the other wells to build a deep learning model. The deep learning model can be used to predict SBED near-wellbore upscaling results for other wells that have petrophysical log and core plug logs, but have not built SBED near-wellbore models yet. For some wells that have the core photos, facies interpretation, and core plugs, we can build the SBED near-wellbore model and upscale it to get the upscaling results, Kx, Ky, and Kz. Then we can convert the upscaling results to well logs so that the deep learning model can be built between the converted upscaling result logs and the other petrophysical logs. After converting the SBED near-wellbore upscaling results to well logs, we can build deep learning model between them and other petrophysical logs. The process of build deep learning model and predicting SBED near-wellbore upscaling results is very similar to the deep learning facies log classification. The difference is here the target is upscaling results, kx, ky, kz, but not facies log. So you right-click on the well and select Build Deep Learning Model. In this dialog, you select the target well log as the upscaling results, which in this case is kz. And then for the input well logs, you can select a bunch of petrophysical logs. You can also do the depth range control and then build the deep learning model. After the deep learning model is generated, you can then predict the SBED near-wellbore upscaling results on other wells using the deep learning model. This is the end of the video of deep learning workflow for well log data. If you have any inquiry, please send message to support@geomodeling.com. Thanks for watching.